we're going to talk about part 3, and we're going to be deriving the transient response. And this is, of course, after the switch is thrown, because that's what we have. So I want to copy this because we're going to need this circuit here. So we can see that the Thevenin RC circuit is a series circuit that requires the use of KVL. So we're going to use KVL to set up our differential equation so that we could solve for VC. So I should expand this. That requires the use of KVL to derive the first order equation. And I really should be saying the first order differential equation, but I'm just going to say the first order equation. Now, one thing that you want to remember is that a series circuit has the same current, through all elements. So in this case, we're going to say that the current of the resistor must also be the current through the capacitor, but we know how to write down the current of the capacitor with the capacitor equation. So if I paste in my Thevenin circuit, what we're seeing is that our capacitive current, which is also the current of the resistor, is this guy right here. So here we go. I'm going to apply KVL. So applying KVL, we see that the source voltage has to be equal to the voltage of the resistor plus the voltage of the capacitor. But the voltage of the resistor, according to Ohm's law, is this guy right here. And if we replace it with the capacitor equation, we get RC of dV dt plus Vc. So this is not a nice equation yet, so we want to put this into proper form. So to put this into proper form, we're going to isolate the Vc dt term. So if I do that, all I'm going to do is just manipulate this guy a tiny bit, divide both sides by RC, and you're going to see that I'm going to get dV dt, and there's RTHC VC, and then I'm going to get VOC divided by RTHC. So this first order equation or first order differential equation is what this is our Thevenin RC first order equation. So this is what we want to focus on. And what you're going to find later on is that the Thevenin RC first order equation is very similar. I don't want to say very similar. Has the exact same form. To the Norton RL equation. So it's useful now to rewrite this equation in dummy variables because we're going to use it in the future. So what we'll do here is that we're going to say that x of t is our storage element. Later on, it's going to be the inductor current. And then we have our time constant tau, which we call RTHC. And then I'm going to define the constant on the right side, the source divided by tau, as VOC divided by RTHC. Now this is a little bit close, so let me bring it down a bit. And this is what I want to highlight. So this right here are our dummy variables. And we'll use these after we rewrite that. As we'll see here that this will pay big dividends later on. Well, this is going to be new nomenclature for the first order equation. So this translates the first order equation to this. So I'm going to have dx dt plus x over tau, and this is going to be k, but k here, to remind you, is constant. It's a constant source. So this is the equation that we want to solve here. So to solve for the storage element, we have to isolate all the x terms. So to solve for the storage element, variable x, one isolates the x terms. And integrates. So let's do that. So we start off with our first order equation. And the first thing that we have to do is that we have to isolate x. So when I isolate x, I have to bring all of the x terms over to the left side, which gives me x minus k tau dx, and this will give me minus dt over tau. Now that I have that, we then now need to integrate this equation. Now this equation is an indefinite integral. And because it's an indefinite integral, we know that there has to be an integration constant. Now this integration leads to a natural log, right? Leads to natural logs, which can be undone by taking the exponential of both sides. So once again, I integrate this thing, so I should have a solution that's a natural log. So I'm going to get the natural log of x minus k tau, and that's going to equal to minus t over tau plus this integration constant. So the next thing that I have to do is that I have to take the exponential so that I could solve for x. So I'm going to take the exponential of both sides. And when I do that, I'm going to get x minus k tau. And this here, if I take the exponential of two functions, it's the product of the two. So then I'm going to get e to the constant times e to the minus t over tau. And then I'm going to redefine the constant as a e to the minus t over tau. So once again, if I look at this constant and that constant, we're going to say that we have redefined the constant to read a. Finally, if we isolating x of t, one arrives at x of t, which is k tau plus a e to the minus t over tau. This is what I call the general response. Remember, you can call it a solution, but it's not a complete solution. It's not a complete response. So let's talk about the language so that you know where I'm coming from. The language is that This is not a solution since we have an unknown constant A. That's why I call it a general solution. In order to get a solution, we have to apply the initial condition to determine A. So what I'm saying here is that to determine the unknown constant A, which is the integration constant, one has to apply the initial conditions. Since we have not, this is a general solution, not a complete solution. So to maximize the general response, so to maximize the power of using the general response later, what I mean later with the inductor, I will determine two constants. So the first constant is that we have to get the initial condition. So we have to apply the initial condition x of 0 minus to determine A. That's what we got to do. Now there's a second constant, and typically I call this a, so we're going to solve for a convenience constant. We don't have to, but it makes things a lot nicer if we do, which will be x at infinity. So let's do that. So let's start with the constant A. So if I'm looking at the constant A, I'm then going to apply the initial condition to determine A. So I'm looking at x of t equal to 0 minus, which is x at 0 minus, that has to be k tau plus A times e to the 0. This immediately tells me that my A constant is now x of 0 minus minus k tau. So that's my first constant right there. So now I'm going to look at the convenience constant. From the general response, we're going to look at the limit as t approaches infinity of x of t, which then means that you're going to see here is that as this does this, I'm going to get k tau plus a to e to the minus infinity. And of course, minus infinity is 0. So then this tells me here that I can rewrite x of infinity to equal k tau. Now I'm armed with my two constants, so now I can finally get my solution into the right form. So finally, the first order solution is written as x of t, and we saw that we wrote this as x of tau plus a e to the minus t over tau. And if I plug in my a constant, I'm going to get k tau plus the quantity x of 0 minus k tau of e to the minus t over tau. But k tau is x infinity. So if I put that term in, we could then say that this will be x at infinity plus the square bracket x0 minus x at infinity times e to the minus t over tau. And this right here is our complete response. And it is this equation that we want to take to the RL circuit. And the language reads something like this. So you'll see that I'll talk about this a little bit more later on. Some textbooks call this the forced response. And they call this guy here the natural response. And we're going to get a lot more into detail of that. So now if I apply this to the capacitor, the complete response, why is it the complete? Because we solved for the constants. Is VC of t is then going to be VOC plus the bracket VC of 0 minus VOC e to the minus t over tau, where tau is equal to RTH times C.